In this video, we're going to talk about the least understood area of fluid mechanics, and that is turbulent flow. And we are going to restrict ourselves to the very basics of turbulent flow. This is just an introductory lecture, and we're only going to talk about fully developed turbulent flow. So just getting started with the review, we know that for a pipe flow with a Reynolds number of about 2100, or lower than that, we usually have laminar flow, right? And then the flow begins to transition to turbulent conditions. We have turbulent bursts or spots within the transitional region. And when the Reynolds number exceeds approximately 4,000, the entire flow field becomes turbulent, and the flow remains turbulent then. And there's a lot of fluctuations, a lot of random turbulent fluctuations within this turbulent flow. So let's just go and look at this turbulent flow now. If I was to, let's say, look at this flow within a pipe, and I was to identify some point within this pipe, let's call this point A. Now, when the flow is flowing through this, and I'm looking at this in time, so the flow is changing in time, and the velocity, let's say, if I was looking at the x component of the velocity, which is represented by u. So if I was looking at the x component of the velocity u at point A, it would keep changing for a turbulent flow. And in a way, graphically, I could represent it like this. So over time, I'm looking at, let's say I'm starting off with at initial time t naught, and I want to, let's say, take a time interval of t, and I want to see what is happening with this flow and what is the behavior of this x direction velocity until we reach time t naught plus capital T. So if I was to look at it within this region over time, obviously there's fluctuations within the value for this velocity, this x direction velocity. But another thing that I can identify is that there's so many points within this, and if I was to take an average of all of these points, it would have to lie somewhere between the highest velocity that is experienced at this point and the lowest velocity, right? So between time t naught, let's say, from this point onwards until we reach this final time, I would have to identify what is the highest velocity and what is the lowest velocity, and then the average velocity, the average of all of these points, the average of velocities at all of these points over time will be somewhere between this highest point and this lowest point. So let's say it's somewhere here, and I can point it out here. Let's say this is the average, and let me represent this average by u bar. Okay, so I can draw or represent this average velocity as a constant, right? Because the average doesn't change; it's the mean value. It's the time averaged value, mean of all of these values. So what this means is that if I was to, let's say, if I'm specifically looking at some point, let's say I'm looking at this point now, and I call the velocity here, let's say I call the velocity at this point u at some time, which is t, then I could represent this velocity in terms of the average velocity, right? Because this is the average velocity, right? So I could represent it in terms of the average velocity plus this portion of the velocity, this portion of the fluctuating velocity. And let's say I represent this fluctuating part of the velocity by u dash here, okay? So if I was to just add this average velocity to the fluctuating part of the velocity, then that would be the same thing as this velocity for this point, right? So this is all we need to develop the basic understanding of a turbulent flow in terms of its velocity. We're looking at the x direction velocity because this is the overwhelming portion of the velocity. Obviously, we would have velocity in the other two dimensions as well, but this is the one that has the major effect on the overall velocity of our flow. So I'm taking the time average, okay? I've just represented this expression over here in terms of an equation. I'm taking the average of velocities at all of these points and averaging them over time t. And over here, I'm writing the velocity at this point in terms of the average velocity and the fluctuating part of this velocity. And this is basically what is called Reynolds decomposition, because he was the one who actually came up with this idea that in order for us to represent turbulent flow, we can go with this kind of expression. Because the thing is that with turbulent flow, there's so many variables and so many parameters that we cannot account for. So we have to simplify things. And in order to simplify things, we look at the average of the values instead of looking at the local instantaneous values of velocity at certain points. So this is called Reynolds decomposition. And if I was to, let's say, show you this and review this again, just to recap this, you would have velocity, which is being represented by the time averaged or the mean value, which is, like I said, u bar. And then the fluctuating part of the velocity comes in as well, and obviously that would be different at every point. So I have the time averaged value of the velocity, u bar. I have the fluctuating part of it, which is u dash. And now it's important to identify that if I was to take an average of u dash, which means that if I was to take an average of all of these fluctuating parts, let's say, what would be the value for that? So all I have to do is, if I was to take an average of it, just like I've done over here, all I have to do is, instead of inputting the value for u dash, I just substitute it by this expression that I've already found out, okay, in this form here. So I just substitute it here, and now I can simplify it. I can simplify this integral, and I do that by opening up this integral and integrating, first of all, u itself, and then integrating the time averaged value. So why does the integral not apply onto u dash? Because it is a time averaged already. Okay, it has a constant value. It doesn't need to be within this integral because it's a constant. So this pops out of here, and all we're left with is dt here. And within this integral, we have u dt, which is the same thing as this. So all we have to do is we just substitute, instead of u dt, we substitute by u bar, and we simplify this integral, which comes down to t, because t naught and t naught cancel out, and all we are left with is 0 now. So what that means is that if I was to take an average, if I was to take a time average of the fluctuations, then that will be 0. And that is important because what that means is that fluctuations are basically equally distributed on either side of the average. And that is easy to understand, right? Like if I was to, even if I wasn't looking at the time average, if I was to, let's say, look at numbers 2, 4, 6, 8, 10, and 12, let's say, just like this is, I'm just trying to make a simple example so you can understand. If I was to take an average of all of these, the average would be equal to 7, okay? So half of these numbers are on the lower side and half of these numbers on the upper side of it. And they would basically, if I was to bring this analogy now here, what I can say is that the average here represents the mean, right? That means that there has to be equal amount of values on both sides of this average. Okay, because the fluctuations are being equally distributed on either side of the average. So that is just an important point to understand. And now if I was to represent all of these onto another diagram, if I was to, let's say, see u dash here, which is the fluctuating part of the velocity, if I was to look at this, and what I've essentially said is that if I was to take an average of all of these fluctuations, it would be equal to 0. Okay, this is at 0. So that is the first point that we need to identify. The second point is that if I was to take a square of these fluctuations, okay, so let's say I'm looking at this one right now. I'm looking at u dash here. If I was to take a square of u dash, I would get naturally a higher value, right? It would be positive. So if I was to take a square of u dash, I would get some positive value. It would be higher than u dash, of course, and it would be positive. The other thing is that even if I was taking a square of u dash when it's negative, let's say if I'm taking square of this fluctuation here, this is negative right now. U dash over here is negative, but what that means is that if u dash is negative, even if I square this up, I would still get a positive value. So that is being represented by this dashed line here. Okay, so what that means is that now if I take an average of all of these, basically of the square of the fluctuations, okay, if I was to take an average of these dotted lines here, okay, it would be, I don't know what it would be, but it will be, again, it will be something positive because all of these lie in the positive region somewhere. So because there's these are fluctuations, these cannot be 0. So because the fluctuations themselves are not 0, that means the average is going to be a positive quantity as well. And average I'm representing by the bar here, okay? So the average of the square of the fluctuations is going to be a positive value. It's being represented by this dashed line here, okay? So again, I have the average value and something by Reynolds decomposition that I got, which is u dash. And then if I was to take a square off this fluctuating part, it would be equal to this, which would be greater than 0. So the question is, though, that why are we doing all of this? And the reason is that these fluctuations vary, right? So for different types of flow, It's entirely possible that these fluctuations are of a higher order, or it's entirely possible that these fluctuations are not that much. And what that means is that it indicates that what is the level of the turbulence within our flow, that how turbulent is our flow, okay? The question is that what is defining this turbulence? How turbulent is our flow? That is what we need to identify. And to identify that, we need to find out the level of turbulence within our flow. And to find out the level of turbulence, we basically need to get to this expression, because what we essentially need is the square root of this expression. And the square root of this expression, the square root of the mean square of the fluctuating velocity, it's also called something which is called root mean square. You must have heard of it before, root mean square of the velocity. So this is the root mean square of the fluctuating velocity. And if we divide it by the average velocity, that gives us something called the turbulence intensity. Okay, the turbulence intensity, and it's also represented by I, you will see in some texts. So turbulence intensity is the variable that we need in order to identify how turbulent our flow is, in order to identify the level of turbulence of our flow. And usually this is somewhere between 1 to 10%. This is in the form of percentage, okay? So this is usually between 1 to 10%. The lower the value of turbulence intensity is, the lower the fluctuations of the velocity are. And the higher the turbulence intensity is going to be, the larger are going to be the fluctuations in this velocity, okay? And that means in other flow parameters too, in terms of pressure head or flow rate and stuff. So just to give you an idea of what a turbulence intensity looks like, for really well-designed wind tunnels, you would usually have a turbulence intensity of 1%. And let's say if you're using some fluid flow softwares like Fluent, you would see that by default it's adjusted at 5%, and 5% is an okay value. 10% or higher, that's a lot of turbulence, and so we take this as the default value in our fluid flow softwares. So this is what the expression for turbulence intensity is, and now we need to move on, and we need to go back to understanding the shear stress concept, and we need to apply it to the turbulent flow. So for laminar flow, we've identified previously, and we know that this is the expression that is valid for a Newtonian laminar flow. And it is tempting that we extend this same concept of a laminar flow, of shear stress for a laminar flow, to the turbulent flow as well. But because of experimental and theoretical studies, we know that this is actually not correct for a turbulent flow. So what we need is, we need to understand physically what the behavior for a fluid looks like and what produces shear stress in the first place, okay? So if we were to look at laminar flow here, let's say. So laminar flow is usually modeled as fluid particles that are flowing smoothly along in layers. They're gliding past each other. Some are slightly slower, or faster ones are on either side. And this is what's the usual representation, right? So this is, first of all, we had the entrance length. That is why the velocity was changing there. And then we have the fully developed laminar flow, where the velocity doesn't change anymore. And we model it as the fluid particles flowing smoothly in layers, they're gliding past each other. Some are slightly slower, the ones at the ones that are closer to the wall, and the ones closer to the center line are going to be faster. But what we need to remember is that actually the fluid consists of a lot of molecules that are actually like the molecule here and the molecule here that are actually moving about randomly, moving about in a random fashion. But this motion is not entirely random. So for example, if I was to take this plane, if I was to look at how this molecule would move across this plane, let's say, what would happen is that the molecules that are moving upwards from here, okay, they have a lower velocity. They're coming from an area where the velocity is lower than the ones that are present here. Okay. And now these molecules, these are small, and because this molecule with a smaller velocity is moving up, so this is creating an effect onto the molecules that are above it. Let's say a molecule that would be here, it would have an effect on this because this molecule is now moving with a faster velocity as represented here, and this molecule is moving with a slower velocity. And because of these two, because of the movement of these two, shear stress is produced, right? This shear force is only present here because there is a gradient that exists here in the velocity profile. Otherwise, if this wasn't happening, if there was no gradient here and the velocity was similar, then there would be the x component of the velocity and the momentum as well between the upward molecule, which is here, and between this one would be the same, and we wouldn't really have any shear force present. But for the shear force to be present, these are moving at different velocities. So by combining this effect, by knowing that as a whole, as on a macroscopic level, we imagine that these fluid particles are flowing smoothly along in layers. But on a microscopic level, we know that these molecules are actually moving about randomly. But this is not so random actually, because they're only moving like this because of the interaction with the particle that is next to them. Okay, and this is exaggerated. This distance is exaggerated. This would be a molecule that will be present right next to it. And this velocity profile doesn't show you the full velocity profile. Of course, it's just showing you a part of it. So this is what gives us the Newtonian viscosity law, which is this one here. And this is how we model laminar flow based on the value of mu here, which is related to the mass and speed because of the temperature of the random motion of the molecules. And although the random motion of the molecules is also present in turbulent flow, there is one factor that is more pronounced, because of which we cannot use the same relationship. Okay. And the simplest way of thinking about turbulent flow is that we look at it in terms of eddy motions, in terms of eddy type of motions, okay? In terms of these turbulent eddies, because of which these molecules, these not molecules, I wouldn't call them molecules. This is not happening on a microscopic level anymore. This is mixing that is happening in here. So how is turbulent flow different from a laminar flow? For laminar flow, the molecules were moving randomly on a microscopic scale. But for the turbulent flow, we have these three-dimensional eddy type motions, and these eddies range from very small diameters that would be as small as the fluid particles to fairly large diameters, which would basically give us the macroscopic look here. And they move about randomly, so they are not only moving with changing velocities, but they're also moving the mass, let's say. They're also moving a chunk of mass from this place, let's say, to some other location within the flow. And because the transport of momentum is happening now, this finite chunk of fluid is moving, okay? Remember, in laminar flow, we didn't have this happening. The finite chunk of fluid wasn't moving. Yes, random motion of molecules was happening. That was on a molecular level. That was on a microscopic level. But now we have, let's say, this entire chunk of fluid here, which is moving from one place to another. This is being randomly transported, let's say, across this plane, and this is being randomly transported here, and that results in a relatively larger shear force. Okay, so instead of just the molecule moving, we have a fluid element that is of a much bigger size. It's actually a finite chunk of fluid, and these chunks can vary in size, but they're a lot larger than molecules. So because of these, now the shear stress for a turbulent flow would be a lot higher. Okay, it would be a lot larger than just this. So what I can say is that because the shear stress for a turbulent flow is a lot higher than this, and from experimental studies and theoretical conclusions, I'm not going to go into the detail of them. I'm just going to restrict myself to just telling you, to just giving you this information that this random momentum transfer that is happening here, this is based on u dash. This is based on the x component of the velocity in conjunction with the y component of the velocity, let's say, because this is interacting with the shear force, and this is interacting with the rate of mass transfer that is happening across this plane, sorry. Okay, so in other words, because I said that the turbulent flow shear stress, the turbulent shear stress is a lot higher than just this one, so I can write this turbulent shear stress in terms of this value plus some additional value, okay? And this value I already know. This is laminar shear stress. So I just have to, let's say, add this some other value, and I call this some other value the turbulent shear stress, okay? And I add the two up, and this would give me the total shear stress for a turbulent flow, okay? And what is actually found out is that because, like I already said, the fluctuating part of the velocity, the u component and the x component and the y component, they're the ones that are causing this additional term to develop. So when we write this tau equal to this value here, okay? And this is going to give us the turbulent shear stress, okay? So this is giving us the turbulent shear stress. So turbulent shear stress is equal to this value here. And this is called Reynolds stresses, okay? Any stresses that are of this form are called Reynolds stresses. They're you can check the units as well. They're in Newton per meter square. These are called Reynolds stresses. And why are these called Reynolds stresses? Because Reynolds was the first one who discussed these stresses in 1895. So from this, what we can see is that shear stress in turbulent flow is not just proportional to this component here, but it also contains a contribution here because of the random fluctuations of the x and y component of the velocity. And the density is involved here because like I said, larger chunks are moving, okay? Because finite mass is moving here within the turbulent flow, and mass is represented by density for fluids, okay? So this is how we relate turbulent shear stress. But the thing is that this expression here, it's hard to determine these Reynolds stresses. It's hard to determine their values. So we need some other expression. We'll move on to that in a minute. But before I move on to that, I want to show you what this shear stress is going to look like graphically, because we've already seen that this has a linear relationship. For a laminar flow, it increases in a linear way as we get closer to the wall. So if the wall is here, a linear relationship develops. So we get tau W here, which is the tau wall, which is the highest shear stress, and at the center line we have a value of 0 for the laminar shear stress. But for the turbulent shear stress, how is this going to be represented, and what is the structure of the shear stress? So let's just look at that first. This is what it looks like. And now this is an entire theory within itself. I'm going to stop this video here, and we are going to move on to looking at what this is about and how the velocity profile looks like for a turbulent flow, how the average velocity profile looks like in the next video. But the basic understanding has been developed, and we're also going to look at the expression for this turbulent shear stress in some other different kind of model, because the thing is that the expression that we talked about here previously, let me just erase this, the expression that we talked about here, this one, this Reynolds stress cannot be accurately determined, okay? Because the fluctuations, they're changing so quickly and so fast that even super fast computers cannot determine what these are going to look like. It's equivalent to not even basically knowing, because the thing is that we have to plug this into the momentum equation, and then we have 3 different kinds of Reynolds stresses in that equation, in the momentum equation. We're not going to go into the detail of it, but still I'm going to show you a model in the next video of what this Reynolds stress can be changed into for an easier understanding and use.